Okay, let's get started then. So for those that missed last week's class, I went through a bit of a course outline, navigate through the course website, and then we did a bit of introduction to management science. We formulated some basic programming models, and now today we're going to try to solve some of those models, perform some sensitivity analysis, right? So I'm just going to use the same examples we did last week. That way you already know what the example is about. But last time we just formulated the model. We didn't actually solve the problem. And so today we're going to solve the problem. And we're going to also perform some sensitivity analysis on the constraints. So this is the Mgoc10 problem that we formulated last week. And so just to recap, Mgoc10 mixed with toy soldiers and trains. So x1 is the number of toy soldiers we make, x2 is the number of toy trains we make. We want to maximize our profit function z, and there were some constraints. Total finishing hours not be more than 100, total carpentry hours not more than 80, and you can't sell more than 40 soldiers, so don't make more than 40, and that the variables cannot be negative, right? So that was the model we came up with. So now we're going to solve it. Before we do it, gotta introduce you some terminologies and concepts. So it says any specification of the values of the variables is called a solution, right? So any value of x1 and x2, we call it a solution. So for example, x1 is 60, x2 is 10. Well, this is not a very good solution because, as you can see, if x1 is 60, it violates the soldier demand constraint, right? So that leads us to the idea of a feasible solution. So a feasible solution is a solution that satisfies all the constraints. So for example, if you plug in x1 is 40, x2 is 20, it will satisfy the constraint. x1 is 30, 25, x2 is 20 over 1, it will satisfy all the constraints. So there's a whole bunch of feasible solutions out there for the problem. And then the set of all the feasible solutions, we call that the feasible region. Right? So we are trying to maximize this profit z here. So given there are many feasible solutions, the goal is to find the best or optimal solution. And what is meant by optimal? Well, that depends. For maximizing problems, such as maximizing profits, the optimal solution or the best solution is one that maximizes the objective z value. For a minimization problem, if this is minimizing cost, then the best or optimal solution is the one that minimizes the objective value z. Solutions which are the intersection of two or more constraints are called corner feasible solutions. For example, you have two equations here. You can set it to equal, you can solve it, and that point will be at the intersection of the two lines. So we call those corner feasible solutions. On the graph, it appears actually on the corners of the feasible region. So the theory says the optimal solution for the problem, if it exists, must be a corner, and so you don't really need to waste time looking elsewhere, right? So in general, your model can have one unique optimal solution. It may have many multiple optimal solutions, or the problem can be classified as infeasible, in which case there's no feasible solutions, or the problem can be classified as unbounded, in which case the objective goes to infinity or negative infinity. Once you have solved your problem, you can calculate some slack and excess for each of your constraints. Switch out my glasses here. Okay. Okay, I have my glasses in the drawer, so I'll get it later, I guess. Okay, so once you solve the problem, you can calculate the slack or excess for each of the constraints. And slack is calculated for less than or equal to constraints, like such as this one here, right? And basically, as you can see, the right-hand side is always bigger than the left-hand side. So we take the right-hand side and subtract the left-hand side, and we get the slack. So for example, if you solve the Mgoc10 problem, the optimal number of soldiers and trains to make is 20 soldiers and 60 trains. we had 80 hours of carpentry time available to us. So in the optimal solution, did we use it all up? Do we have any slack or unused hours? And so we take the right-hand side and subtract the left-hand side. We put in the optimal values, and we have 0. So which means in the optimal solution, we used up all the carpentry hours. We used up all the carpentry hours. Also in the model, you could make up to 40 soldiers. And so in the optimal solution, did you do that? Or did you have some slack or unused room? So again, we take the right-hand side and subtract the left-hand side, and we have 20. So that means I could have made up to 40, but I actually have 20 unused rooms. Right? So basically, slack measures unused resources, unused rooms, and so on. Okay, so something along those lines. You know, I remember it was maybe 18 years ago, 15 years ago, one day I wake up and I'm eating a box, some cereal, and all of a sudden the box of cereal looks just blurry to me. I have my glasses on, and it's like, whoa, what happened? And so I went to the eye doctor and said, I think I'm going blind. Something's weird. Like I can't see close anymore. And the doctor said, well, it happens. You turn old. And for some people, it's a gradual thing. And for some people, it's, just overnight. One day you see, one day you don't. So it was a really strange feeling, Okay, another measure you can calculate is excess, and excess is for greater than or equal to constraints, like this one here, right? So we would be calculating the slack for this constraint, and we'd be calculating the excess for this one and this one. And as you can see, for greater than or equal to constraint, the left-hand side is always bigger than the right-hand side. So to calculate excess, we simply take the left-hand side and subtract the right-hand side. So this is the M&D Chemical Company example that we solved last time. So here we have to determine how many gallons of chemical A or product A to produce, and how many gallons of product B to produce. We want to minimize the total cost of producing A and B. We have to produce at least 125 A. We have to produce a total of 350 B, and the processing hours cannot be more than 600. So if you solve this problem, the optimal solution is to make 250 A and 100 B. And so we can calculate excess for some of the constraints. For example, we have to make a total of 350 gallons combined. So in the optimal solution, do we end up making any extra or excess? So again, we take the left-hand side and we subtract the right-hand side, and that works out to 0. So we had to make at least 50, we made exactly that, we didn't make any more. We had to produce at least 125 A alone, and so in the optimal solution, did we make any extra, surplus, excess? So again, we take the left-hand side and subtract the right-hand side, and we get 25. So this tells us that in the optimal solution, we make 125 gallons above and beyond what was required. So basically, excess measures surplus, extra, above and beyond, that kind of idea. Okay? So excess measures extra, surplus, above and beyond requirement. Finally, it says over here, given the optimal solution, a constraint is said to be binding if the left-hand side equation is exactly equal to the right-hand side equation, right? So for example, this constraint here is binding because when we add a plus b, we get 350 on the left side and it's 350 on the right side. So it's a constraint, the left side is exactly equal to the right side, we can't say that constraint is binding. And for any binding constraint, obviously the excess or slack would be 0 because the left-hand side is exactly equal to the right-hand side. Okay, let's look at another problem here. So this is a 2 products 3 machine problem. It says a company is produces 2 products using 3 machines. Okay. So you can see here, each unit of product 1 uses 1 hour machine 1, and then 3 hours for machine 3, and you get $3 per unit. Each product 2 uses 2 hours for machine 2, 2 hours for machine 3, and $5. And the number of hours available for machine 1, 2, 3 to produce the product is 4, 12, and 8. So the idea is that the products, they need to go into machine 1, and then they go into machine 2, and then they go into machine 3 before they're completed, all right? So these hours here represent the amount of time that they need to spend in the machines, right? Okay, formulate an LP model, determine the number of product 1 and 2 produced to maximize the total revenue. So we're going to let x1 and x2 be number of product 1, 2 to make. And then in terms of constraint, basically, it's just like, we cannot use more hours on each machine than is available to us. So for example, well, before that, we'll maximize the profit. So that is basically 3x1 plus 5x2. And then in terms of the constraints, so we cannot use more than 4 hours on machine 1, cannot use more than 12 hours on machine 2, and so on. So basically, total hours used on machine 1 cannot be more than 4 hours. So what's the equation for that? Total hours used on machine 1 cannot be more than 4 hours. So what's the equation for that? Really that hard? Really? Okay, well, if you look at machine 1, each product 1 will use up 1 hour, and product 2 doesn't use up any hours. So basically, x1 is less than 4. Similarly, for machine 2, total hours cannot be more than 12. So for machine 2, product 1 doesn't use any hours on it, product 2 uses up 2 hours. So that means 2 times the number of product 2 produced cannot be more than 12. And then finally for machine 3, well, what's the equation for machine 3?
$3x1 plus 2x2 less than or equal to 18.
Yes. 3x1 plus 2x2 less than 18. And then of course you cannot produce negative products, so x1, x2 greater than or equal to 0, so that's a very simple model there. Okay, so now in part B it says solve the problem using graphical method. Okay, some people like to just use the graph on their own tablet, or some people like to have a graph paper, so if you want a graph paper, let me know, or you can just use the graph on your own, whatever, tablet. Couple more here. Sorry. I'll come to the other side. Anyways, if you change your mind, you can come help yourself here. Okay, so let's solve this problem together here. Okay, we'll put down the problem here, because we're gonna need to use it to put down points and so on. So let me just put the problem down here. Okay, and I'm gonna put on my graph here. I'm gonna put x1 over here, and then I'm gonna put x2 up there. Okay, so let's start putting down the equations. I got the first one here, x1 less than equal to 4. So x1 equal to 4 is right on the line here. So, but then on the line is equal to 4, but I want less than equal to 4, so am I looking at the area on the left or on the right? Left or right? Left, right? So I just put a little indicator here that I should be on the left of the line. Okay, next, I have a 2x2 less than equal to 12. So 12 divided by 2 is 6. So we have x2 less than equal to 6. Again, right on the line is 12, but I want it to be less than. So top or bottom? Bottom. Okay, next I have this 3x1 plus 2 less than equal to 18. So what I do is I pretend is equal to 18. Okay, I pretend it's equal to 18. And if that's the case, if x1 is 0, what's x2?
9.
On the other hand, if x2 is 0, what's x1?
6.
Okay, so I have 2 points. I can plot 0, 9, 6, 0. Okay, so 0, 9, 6, 0. Again, right on the line is exactly 18, but I want less than. So, to the left or to the right? Left or right? Left. When in doubt, put a point on the left. For example, let's say we put 2, 0, right? That's on the left, right? We put 2, 0. And you can see if x1 is 2 and x2 is 0, you get 6 less than equal to 18, so correct. It's the points on the left. So now, everything in this shaded area satisfy all my constraints. Right? It's to the left of this, to the bottom of that, and so on. And so this is what I call my feasible region. Okay, so that's what I call my feasible region. Now, some of your other math courses, they teach you to shade the other side. I don't really care, okay? Shade the inside or the outside, one way or another, you know, it shows where the feasible region is. Then these corners of the feasible region are what we call the corner feasible solutions, right? They're an intersection of 2 or more constraints. So, you know, this one here, intersection of this one here, intersection of this and this, okay? So these over here are called my corner feasible solution, right? And again, the theory says if the optimal solution exists, it has to be a corner, okay? If it exists. So the question is, you know, which one is the corner? And to figure out which corner is the optimal solution, we have to put in the objective function line, okay? We have to put in the objective function line. To graph the objective function line, you need to give it set it to some number, okay? So maybe for the first line, I'll set it equal to 30, okay? Or maybe for the first line, I'll set it equal to 30. If I do that, if x1 is 0, what's x2? 6. On the other hand, if x2 is 0, what's x1? 10, right? So I have a 0, 6, and 10, 0. To solve the problem, you need to have 2 objective function lines to see what's going on. So I will then create another one. Okay, you would need to have 2 objective lines to see what's going on. So this one I'll set to 15. And so if x1 is 0, x2 would be 3, and if x1 is 5, sorry, x2 is 0, x1 is 5, okay? So I have two lines here. Yes?
Sorry, why are you setting it equal to an area?
First of all, you have to set it equal to a number to plot it. And secondly, I chose 30 because it's divisible by 3 and 5, I don't get decimals. I mean, I could put 300 here, but then I would get 60, which isn't very good for me either.
So, sorry, so you just put like the smallest number that would be.
I choose some number that makes it easy for me to put on the graph. Okay, so line 1, 0, 6, 10, 0. Okay. Okay, so this has a objective value equal to 30. And my other line was 0, 3, 5, 0. And this has a objective value equal to 15. And of course, these are parallel lines that come from the same equation, right? So I'm trying to maximize my objective value, so I want it to be as high as possible, right? So I see, okay, here's the objective line is, here is 15. If I move over there, it has a value of 30. So I know this is my direction increase in Z. This is the direction I want to go. Okay, this is the direction that I want to go, right? That's why you need two lines so you can see the direction you need to go. So how far can you go? Well, you have to stay in the shaded area, right? You have to stay in the shaded area. So it looks to me like the farthest you can go would be that point there, okay? The farthest you can go would be that point there. And so, that would then be your optimal solution, right? So it looks to me like the farthest you can go is that point there, and so that becomes your optimal solution. And we can read out the optimal solution is x1 is 2 and x2 is 6. Okay, so solving the problem, the optimal solution is x1 is 2, x2 is 6. And z is then 3 times x1 plus 5 times x2. So 3 times x1 plus 5 times x2 gives me $36. Okay, so that's how we solve the problem graphically here. Okay, so let's go back to the problem. it says, perform some sensitivity analysis on what happens if you have more machine 1 hour and more machine 2 hours. Okay, so essentially we are originally for machine 1, so we'll do machine 2 first, okay? So initially for machine 2, the constraint was 2x2 less than equal to 12 hours. So it says, okay, so what if we have, say, 14? Okay, so what if we say we get 2 more hours on machine 2, right? So we are basically changing the right-hand side values of our constraint, right? And that's why in the topic here, we're doing sensitive analysis of the constraints, right? Because we're changing the right-hand side values of the constraint, right? So question is, what if you get 2 hours more on machine 2, right? To figure out what's going on, we need to rough in our graph. Okay, so we have this constraint, we have that constraint, and we have this constraint. And then we had our feasible region there, and then we had our optimal solution right there. Right? That's the current state, right? So what happens or what changes when I go from 2x2 less than 12 to become 2x2 less than 14? What changes? So when I go from 2x2 less than 12 to become 2x less than 14, what changes in the graph? Yes?
The horizontal line goes up.
Yeah, the horizontal line goes up, right? And so all of a sudden, these points here, they were not feasible before, they now become feasible. So my feasible region expands. Okay, those points that were not feasible before, they're feasible now, right? And so, why be happy over here? When you can move up to over there. Okay. So this is the optimal, and this is the new optimal. Okay, so that was the old or current optimal solution, and then now we are able to have a new optimal solution. Right? And so, to obtain the new optimal solution, we see that it's the intersection of this 2x2 equal to 14 line with this 3x1 plus 2x2 equals 18 line, right? We can solve for that point. So to obtain the new solution, you have to solve 2x2 equal to 14 with 3x1 plus 2x2 equal to 18. And you'll get x1 equals 4 over 3, and x2 is equal to 7. How about the objective value? So the new z will be 3x1 plus 5x2. So now it is $39, whereas the OZ was $36. So basically, we have a $3 change over a 2-hour increase for machine 2. So that is basically $1.50 per hour. This has a name. It's called the dual price for machine 2. Okay, this value or number is called the dual price for machine 2. So what is the dual price, or some people call it shadow price? So maybe a little definition here. So the so-called dual price, people call it the shadow price, is basically the amount of change in Z for 1 unit increase in the right-hand side of that constraint. So this is the amount of change in Z for 1 unit increase in the right-hand side value of the constraint. So this tells me basically if I get 1 more machine hour, I make $1.50 more, right? My Z will increase by $1. This calculation is really just to get the number or magnitude, as whether this dual price should be a positive or negative depends on whether Z is better off or worse off. So in general, if Z is better off, then the dual price is positive. On the other hand, if Z is worse off, then the dual price is negative. So this only gives the number. So you have to adjust whether it be a positive number or negative number based on whether your Z is better off or worse off. And our problem here is Z better off or worse off? Is Z better off or worse off? Better off, right? We made more money, right? So in this instance, since Z is better off, and so the dual price is equal to, I guess if you want to be technical about it, plus $1.50 per hour. But people don't normally put the plus sign there, right? They will put the negative sign there, but they won't bother putting the plus sign there. So, with the dual price, you can also perform some additional sensitivity analysis. Right? And so we could perform some additional sensitivity analysis if we want. So in the original problem, we had 12 hours and the objective was 36. Then we increase it by 2 hours and the objective became 39. Okay, so what if I give you another 2 hours? What's your estimate for profit then? What's your estimate for profit then? Sorry? 42 is correct. So 36, and then we're increasing by 4 hours now, and every hour is $1.50. So it's 42. Okay, we're increasing by 4 hours now. Every hour is $1.50, so 42. How about if I take away some hours? What's your estimate of the Z? 34? Sorry? 33? Well, here I am basically taking away 2 hours, and every hour is $1.50, so I'm going to take away $3, so 33. So, you know, the dual price works up and down the same manner. You give me an hour, you make $1.50 more. You take away an hour, you make $1.50 less. Okay? It works up and down the same way. I'm going to give you 1,000 hours more. I'm going to give you 1,000 hours more. So you do the calculation. And you get 1536. So the question is, do you think it's 1536 or do you think it's something else? Do you think it's 1536 or do you think it's something else?
I think it's gonna be 45.
You think it's going to be 45?
Because there's another constraint for machine 30.
Give it to me in English.
Alright, so there's another constraint, there's 3 constraints, so the
Right.
feasible region, even if you increase machine 2 hours by so much, at one point the feasible region will increase.
Okay, so picture your manager. Never took an LP course, doesn't really understand constraint feasible region. Say something that he will understand.
I don't know how to use words.
Okay? But you're right, but he's not gonna get it, or they're not gonna get it.
Yeah, it's that you need more, you have like limitations in the amount of product too you can make. Like you can't just make an infinite amount of product. Like just having more machine hours isn't going to give it to you, I don't think.
Okay, well, basically it's back to the problem that we have, right?
All right, right.
Making the products need to go through so much three
Yeah.
machines. So if I keep pumping machine 2 hours for you, eventually you make more products initially, but you're gonna run out of either machine 1 or 3 time, right? And then that's it. More hours is not gonna let you make more, and you don't want to make money more. So that's the explanation. Making the products uses up not only machine 2, but 1 and 3 hours as well. And sooner or later, you're gonna run out of machine 1 or 3 hours, and that's where your constraint is, the top. So basically, there's a range, okay? At which you can increase or decrease machine 2 hours. For the dual price to stay at $1.50. Okay, remain at $1.50, and so you can do this math, right? So there's a range. You cannot give 1,000 hour expect the $1.50 to still work. Next time we use the Lingo software to find this range. So as long as machine 2 hours is between 6 and 18, the dual price will be equal to $1.50. Okay, as long as it's in that zone from the Lingo software, your dual price will stay at $1.50. So next week, please bring your laptop, tablet, whatever that you can run Lingo on, okay? So just a little bit intuitive feel on how this range comes about, right? So just a little intuitive feel on how this range comes about, right? So when this, goes to 18, okay, when this goes to 18, the line will be right there. Okay? So basically, so now if you increase machine 2 to more than 18 hours, you're stuck at that point. Okay, you're stuck at that point. It's not going nowhere anymore. And so that's why the range, the upper range is 18, right, for machine 2 hours. Because when you hit 18, the line goes to that point, and you go up anymore, it's stuck there, okay? It doesn't move anymore. So that's how we get the upper range. How does the lower range is 12? The optimal solution is here. If this line shifts down a little bit, then the optimal solution shifts down there a little bit, okay? And if the line shifts some more, then the optimal solution shifts. So moving up along this line is the rate of $1.50. Okay, moving up along this line, $1.50. When you get to here, the optimal solution is gonna, if this keeps dropping, the optimal solution doesn't follow this line anymore. Okay, it has to go down this way. Okay, because the feasible region is here, right? And so this is no longer $1.50. I don't know what it is, but it's no longer $1.50. Okay, and this point here is where 2x2 is less than or equal to 6. Okay, this when it drops down to here is where 2x2 is less than or equal to 6. Okay, so this is $1.50, and when it is, okay, it's not $1.50 anymore. Okay, so that's basically the idea of why those ranges exist, because the feasible solution either gets stuck or it has the optimal solution changes direction. Okay, where's sign G, please? I didn't pass one out? Oh, crap. Okay, well, I'm gonna pass it out now. If you have, please sign in. If you missed last week's class, help yourself some pictures here. And we're gonna have a 10-minute break. Zip copy.
If you want to just DM me on Instagram. I noticed you're in this class. Why are you here? Aren't you fourth year? Yes. So you have OC10 and OC20? Yes. So what happened was third year. So I don't know. I re-deferred it because I had surgery and I gave it well. Yes. But then I was supposed to graduate this semester. Professor Hamlet and me together. So you're doing OC10, OC20? No, I'm doing OC20 this summer. Oh, okay. Yeah, you too, right? Oh no, I'm going to go because I still have 2 more courses. Yeah, so it's like 8 months. Because I'm supposed to graduate like 2026, right? But like, cost delay and whatnot, so I pushed back everything. Oh really? Come on, you're our like carry. You know? No, bro. What do you know? How do I carry? Oh, you've been like yapping a lot in the class. I guess. Maybe. Yeah, let me know. Let me know when you go. If I do, if I am in here now, I'll keep it. The tourist spots are great, but then the fuel is hopefully, I still haven't dropped, so I can see classes. I don't know. It's the report that scares me. Yeah. And I think she has a huge bias for you. What? She has a huge bias for you. Yeah. The tables are like, oh, I was like, that is so Have you been? I took a lot of yeah, I thought something. Where? I didn't know the guy was like, the artisan it's like a third of us. Oh, you know, like I didn't even know. Cause like the stairs only do 2%. Yeah. So we have to take the elevator to get to the 50th floor. I don't do because a friend of mine couldn't walk. So I like kind of walked her. You just sing or like she was doing competitions last week.
And she said she thinks it's more like they just want to gauge like what. We also have some level. But I don't know how to. Oh, I do. Yeah, I don't know all the way. It looks like, oh, it looks like I'm like, I don't know what that means. It's just like, oh, yeah. I mean, there's also, there's like, there's a lot of places. Like a lot of places. So I was thinking about it. It's like, I'm like, guys, everything. But then I was like, I didn't see you like, because if you don't cut your teeth often, you'll
It's just like if you can't have a piano,
oh yeah.
you need to have a lot of like space.
Yeah. Well, no.
Oh,
No, my bad. I should have put it more.
Trip on it again, bro.
I'm gonna trip on it again too, yeah. When I leave, I'm gonna take a full first and then it's gonna break. I so badly just want to speak. Okay. Essentially, how are we gonna take care of our I'm just gonna leave it.
oh, it sounds so.
And guys have been earning well. We can't travel without our passport.
What's happening?
So basically, to get to Mexico, we need passports. But Mexico already involves a lot of swimming. So you can't swim without passports. Where do we leave our passports? The whole state is not that close. Considering how it's probably going to be ghetto too. They're charge us to keep our passports. If we rob our passports, charge us to get it back.
Once you get to the room, just pry the floor and suck them.
You know what? That's not a bad idea. What if we just hired somebody to just stay at home? Like stay at the hotel. We trust a higher person. I could hire my friends, so they'll pay for the plane ticket and everything, you know, just stay at the hotel all day, every day.
Oh yeah, that's what
Pretty much. Why did they switch to this section? Wait, I was in 3 to 5. I was in 3 to 5 for this one, but why did they switch to this section?
I haven't pulled it yet. I'll do it Wednesday after the other
I
class.
can't remember the original one without the
Probably before.
Like I can. Like the
Oh, I already signed
Wait,
it.
what is that? You didn't sign it.
After Wednesday's class.
It's like frozen.
I don't want to.
Bro, I'm not
Yeah.
So you're staying home today, right?
Okay, well, I'm
We're gonna stay over tonight.
Yeah, I can't hear.
Oh yeah. Is it this Wednesday?
Yeah. But, because I want to go back home.
Okay, so let's complete this column here. Okay, so C was perform some sensitivity analysis on what happened if you have more machine 1 hour, machine 2. So we did machine 2. Now we're going to look at adding hours to machine 1, right?
See, I'm gonna see
So what if you get, say, 1 hour more machine 1? So machine 1 hours was x 1 less than 4, and so we're gonna change it to now x1 less than equal to let's say 5, right? So what if you get 1 hour more on machine 1, right? So I'll post the assignment 1 on Wednesday after the Wednesday's class. And you can work by yourself or with one partner. And I show people how to find a partner, you know, if you need to, on the Kirkus course page. And when you do submit your assignment, only one of you need to submit it and make sure you have 2 names on it. Okay, so once again, we have to roughen our diagram here.
every class.
So that's the current situation. So now, if x1 less than or equal to 4, change to x1 less than 5, what changes on the graph here? Yes?
Well, the line shifts and it increases the feasible region.
Okay, so the line shifts like so. And the feasible region expands, right? These points were not feasible before, but now it is, right? Okay, so similar to the machine 2, we see that the feasible region expands. However, as you can see from the graph, it's not going to make the optimal solution change. Right? It's not like the objective function somehow can move higher. Right? It's not like the objective function somehow can move higher. Okay? So the feasible region expands, but it's not really in an area that affects the optimal solution. And so there will be no change. Right? But not in area that affects optimal solution. So therefore, no change. So you can see sometimes when the constraint shifts, you know, when the right-hand side value, the constraint changes, the optimal solution changes. And sometimes when you change the value on the right hand side during the constraint shift, the solution doesn't change, right? So again, your manager says to you, I don't know, are you sure you're doing this right? How is it that I'm giving you more resources, more machine 1 hours, but we cannot make more money. So what do you say to them? Yes?
We're more limited on machine 2 hours. Sorry, machine 2 or machine 3 hours. That's constricting production more in compared to machine 1.
Yeah, but surely you can make some more, just like what we've seen in machine 2.
No,
You can make not a ton more, but you can make some more.
No, because we are more limited on product 2 than compared to product 1. We can continue making more product 1 without any restrictions, but product 2 is what we need to expand for further production.
I don't see it. You can make more product 2, you can make more product 1 with more machine 1 hours, sure. You can
Machine
make more
1
product 2,
doesn't-
you can make product 1, and you make more money.
But machine 1 doesn't relate to product 2. There's no time
Okay, then make
for-
more product 1.
Yeah. If we make more product 1, we're still limited on machine 3 because we require both product 1 and product 2 for that.
Kind of. There's a simpler explanation. Yes?
It's the fact that, more hours of machine 1 affects product 1, but the problem is we're full on machine 3, so we can't actually complete product 1. We can't make more.
You're saying the same thing you say.
Yeah.
Okay, but let me ask you a different question. Let me ask you a different question. Okay, right now, with us, there's never chalk when I want chalk. Okay. Right now, with us producing 2 units of product 1 and 6 units of product 2, how many machine 1 hours are you using? How many machine 1 hours are you using?
2.
Sorry?
2.
2. You're using 2 hours of machine 1. Okay? Using 2, how many hours you got left?
2.
2. So if I give you another machine 1 hour, what you got left? 3. Right? So you say to your manager, look, we don't use up all machine 1 hours right now. So if you give me another hour, we'll just have more left. Right?
We're just changing X.
So therefore, in the current optimal solution, with x1 is 2 and x2 is 6, we use 2 hours of machine 1. And have 2 hours slack or unused. Okay, you have 2 hours slack or unused, right? So getting more hours on machine 1 will not change solution. What's the dual price for machine 1 hours? What is the dual price for machine 1 hours? What's the dual price of machine 1? Sorry? 0. 0, exactly. An increase in machine 1 hours by 1, the Z does not change. The dual price for machine 1 is equal to 0. So there's a relationship between the dual price and whether there's slack or excess for a constraint. In general, if the slack of a constraint or there's excess for a constraint is greater than 0, in which case G1 it is, or a constraint I, then the dual price is equal to 0 for that constraint. Okay? If there's unused resources or some extra surplus, whatever it is, then adding more of that resource gives you no value. The formal terminology is called the complementary slackness condition. Okay, some exercise for you now. And instead of doing example 2, what I would like you to do is do example 3. Okay? So example 3 is a minimization problem, and it's the same football ad, comedy ad problem that we formulated last week, and now you get to solve it. Okay, so please do example 3. Because example 2 is too easy. Okay, please do example 3. And just a note here, example 3 is a minimization problem, not maximization, right? But it's a story in auto, football ad, comedy ad from last time. Before you start, maybe I'll just do a quick recap here of the process. Okay, so we put in our constraints, we indicate which side they need to be on, okay? We shade in the feasible region. We create 2 objective lines, okay? We put them in, you can see the direction we need to move. And then you move as far as you can until you leave your feasible region, and that corner is your answer. Sometimes you might have to solve 2 equations with unknown, and you can't read it, but whatever, okay? So that's the process. Constraint, indicate side you need to be on, shade feasible region. 2Z line, figure out direction you need to go until you hit the point, right? Okay, we need more graph paper. Anybody? Where? There. There's 2. Up there, I guess. Let me grab my card in case I don't want to rip off the wall. Anybody else? Sign-in sheet somewhere? Over here? Anybody not signed in? Everybody signing over here? You over there? gonna put the graph problem up here, maybe that will help you a little bit, maybe. Okay, let me see how many people are done. Still going. Oh, done. Done. Okay. Crunching the final numbers. Got a few things going on. All of them. Okay, getting better.
What did you get? What's your Z? About 320.
Okay, well, I have to continue now. So I'm just gonna show you the answer. I'm gonna post a PDF file, so don't worry, like rushing. Just try to make you understand the problem a little bit here. So I'll just post this PDF file here. Okay, so for the first equation, I got 0, 14, and 4, 0. So that's this constraint here, and we need to be on this side, right? For the second constraint, I got 0, 2, 12, 0. So that's this constraint here, and we need to be on this side, okay? So you need to be above this line, you need to be to the right of this line. So the feasible region is this open space over here, okay? Open space. And now I put in two objective lines, one set at 200, so that's this one here. One set at 600, so that's this one here, okay? So this is 200, this is 600. I want to minimize, so I need to get smaller, right? I need to go smaller. So my direction decrease Z, I need to go this way. How far can you go? Well, you cannot leave the feasible region, so the point is as far as you're gonna get, right? So again, indicate which side of the line you need to be on, shade your feasible region, plot in your two objective lines, and go as low as you can go. Now this is not, you cannot read the answer off the graph, so you have to solve for the equation of this intersection here. And so solving for the intersection of the equation there, I get 3.6, 1.4, and so Z is 320. Okay, any question on that one there? Yeah, I'll leave it up there for a minute or two, and then, like I say, I'll post a PDF.
So what did you do?
You rounded somewhere wrong. You did exactly right.
Oh no, I didn't calculate it myself. Like I got to this point. I just didn't want to ask ChatGPT to calculate.
You don't have to have my 200, 600, you know, you can have your own 2 lines, but the point is you need your 2 lines so you know which way to go, right? Anyways, I'll put it back on if I have time at the end here, but I'm going to move on with the other problems. Okay, so let's go back to problem 2 here. Okay, so x1 greater than 5. Ah, crap, wrong direction, sorry. Okay, so that's my x1 greater than 5 there. And then for this constraint here, I get the points 0, 4, and 4, 0. And I need to be on this side. Okay, so the question now is we shade in our feasible region. So where is the feasible region? Is it A, B, or C? Feasible region is A here, B here, or C there?
None of
There's no physical.
Sorry?
none of them.
None of those. None of those. There's no feasible region. You cannot find values of x1 and x2 that can satisfy your constraints, right? Because if you're in here, you're not out there. You're out there, you're not out there. If you're here, you're nowhere, right? So there, you cannot find values of x1 and x2 that can satisfy your constraints. In this case, we say that the problem is infeasible. So we cannot find values of x1, x2 to satisfy all constraints. The problem is infeasible. Okay? So not all the time there exists a solution to your LP model. Why would you have an infeasible problem? Well, maybe you made a mistake in writing the constraints down. Maybe this should have been x1 less than or equal to 5, but you mistakenly put it as x1 greater than 5. Or you could have conflicting, requirements, right? You're the government, you want to spend at least $5 billion on education, and you want to keep the budget under $8 billion. It is not going to happen, okay? You have conflicting requirements. And so that's why later on in the course, we turn some of these constraints into goals, okay? So that we are able to solve the problem, right? Okay, let's look at the number 4 here. We did 3 already, so let's look at number 4. problem, the first equation, I get the points 0, minus 1, and 1, 0. And in the second equation, I get the points 0, 6, and 3, 0. And I know I have to put in two objective lines, so let's just get it over with. So 2x1 minus x2, I'll set it to be 2. And I get the point 0 minus 2 and 1, 0. And then the second objective line, I'll set it equal to 3. And then I'll get 0 minus 3 and 1.50. Okay, so next put it on a graph here. So x1 over here, x2 over there. Okay, so I have a 0, minus 1, and 1, 0. And then I have a 0, 6, 3, 0. And you're looking at this and go, oh, you know what? I know what the answer is right there, right? Looks like the problem you just solved. I know what the answer is right there. Well, it's not. So unless you put in your objective function lines and go through the whole process, you would know, and you would have guessed wrong. So we put in our objective line then. I got a 0, minus 2, 1, 0. And I have a 0, minus 3, 1.5. Well, I said, you know, let's not have decimal, but to be honest, 1.5 is really not that hard to put on my graph, so I think it's fine. Okay. And so this is 2, this is 3. I want to maximize, I want to go this way. Okay, I want to go there. Okay. And where's my feasible region? Well, it's this this open space up here, right? And so the question is, how far can I increase Z? How far right can I go?
Is it to infinity?
Yep, there will always be points because the field region is kind of wide open area. It doesn't matter how far, you'll always find there will be points on the Z line that will be in the feasible region. Okay? There will be always points in the Z line that's in the feasible region because this thing just goes on infinitely, right? Opens up. So you can move Z as right or high as you want. And so Z is going to just go to infinity. In which case we say the problem is unbounded. So again, no optimal solution exists, and the problem is simply unbounded. How do you get an unbounded problem? You definitely made a mistake in formulating your model, okay? Maybe this one here was supposed to be less than greater than equal to, and you put it as less than equal to. So you will get an unbounded problem. Clearly, you're missing some constraints in your model, because there is no such thing as, making infinite products or whatever it is, right? Okay, now we have our final problem here on example 5. Okay, so final example 5 over here. And this is the exact problem as the two-product free machine problem we have. Okay, it's the exact problem, x1 less than 4, 2x2 less than 12, 3x1 plus 2x2 equals 18. The only difference is this is 5x2 in the objective here, and in the new problem it is 2x2, but the constraints are the same, okay? It's the same as the two-product machine, the constraints same, except instead of 5x2, we have a 2x2, okay? So we would know how to put the problem down. The other thing I want to note is that the objective function and machine 3 has the same slope. Okay? The objective function and machine 3 has the same slope. That's another feature of this problem. Now, everything's the same, so the constraints I know how to graph. The objective function is different, and so maybe I should recreate my two Z lines so I can solve the problem, okay? So I'll set the first one to be 24, 0, 12, 8, 0, and I'll set the next one to be 12. And I'll get 0, 6, 4, 0. Okay, so I need to recreate my Z line because I changed that from a 2 to a 5 to a 2, right? Okay, so now I'm just gonna roughen my graph here. 10, 8, 6, Okay, so I have my previous constraints, so I know what that is. And then I have a 6, 9. Okay, and then my feasible region is the same old as before. And now I have new objective functions to put down. I don't know how it works on your end. Do you cut and paste from example 1 into this? Okay. how classroom has changed so much. Okay, well, and then we have a 0, 12, and 8, 0. And then we have a 0, 6, and 4, 0. And as I say, obviously the 2Z lines are parallel, but it's also parallel with machine 3 constraints, right? It's also parallel with machine 3 constraints. And so now, when you try to move your objective line, you know, in the direction of increased Z, you don't hit just one point, you hit this whole line segment, okay? Because it's parallel, you don't hit just one point, you hit this whole, so basically this point's optimal, and anything in between is also optimal. So basically, any point on line segment 2, 6 and 4, 3 is optimal. And we could verify that this point and this point gives us the same best Z value, right? So I can plug in my point 2, 6. So I will get 3, 2, and 2, 6 gives me 18. And I also can put in my 4, 3. And I also get 18. Right? So just to prove to myself that yes, you know, those two corners are optimal and anything in between gives me the same Z value. I'm not done with you yet. Gonna totally maximize you out today. And so basically, we have multiple optimal solutions. Now I'm gonna make a very slight change to the problem. I'm gonna make a very small change to the problem. Suppose we change the constraint 2x2 less than 12 to become 2x2 equal to 12. Okay, suppose we make that change. Where's the feasible region? Where's the feasible region?
Any point on that line,
Yeah, which line? There's lots of lines.
horizontal line to the axis.
Any point on here? No.
Is it just the top point of the line segment 2, 6?
I'm not following.
Yeah,
What
that
line
point.
segment?
That 1 point, 2, 6.
Right here?
Yeah.
No. What's the feasible region? I'm not asking for the optimal solution, I'm asking for the feasible region.
There isn't a feasible region.
There is a feasible region.
Okay. Try it.
Line between
Line between,
like
give me points.
0, 2 and
0, 2,
sorry, 0, 6 and 2, 0.
and 2, 0.
So 2,
2,
6.
6.
2, 6.
That is correct. It is this line segment between 0, 6 and 2, 6. Remember, you have to be to the left of this line, okay? Left of this, okay? You have to be to the left of this. And you have to be on this. You have to be on this, to the left of this, and to the left of that. Well, this line segment does it all. It's on it, it's to the left of that, and that, right? What is the optimal solution then?
The
Give you the point.
2, 2, 6.
2, 6, very good. The optimal solution is there. Because this is the feasible region, and now you're gonna wanna move as high as you can. Well, you're gonna move until you hit the tip of that corner, and that's the highest you can go, right? So the process is all the same thing. You wanna move in that direction, and basically the feasible region is that line, so you just move until you hit the tip of the line. Okay, so the answer is feasible region is the line segment 0, 6 to 2, 6. And optimal solution is 2, 6. Okay? So that's how you would solve something if it has an equal sign. You have to be on it, okay? Okay, now I'm done with you. Okay, see you guys next time.